So here are the outcomes for the first lesson in trigonometry. We're going to learn some new vocabulary. We're going to talk about radian measure, which is a new way of measuring angles. And we're going to be able to convert back and forth between this new radian measure and degrees, the old way of measuring angles. We're also going to learn how to find the area of a subset of a circle or a sector. And then in a later lesson, we're going to learn about angular speed and linear speed when we start having a circle rotate. The first set of basic review is to remind you of some vocabulary for angles. The two rays that create an angle meet at the vertex. A small angle is called acute, and a large angle is called obtuse. And acute is anything that's less than 90 degrees in measure. Obtuse is anything greater than 90 degrees in measure. And then the two special cases are straight angles that go straight across. That's 180 degrees. That's a straight angle. And then we have perpendicular lines that form right angles. And so if your diagram has that little box symbol in the corner, it's 90 degrees, which is a right angle. All right, before we can start, let's look at a circle. If I draw on this circle a radius of length 1, I have what's called a unit circle. A unit circle has a vertex, a center at 0, 0, and a radius of length 1. If I draw on another radius, those two radii form an angle. Those two radii also cut off what's called an arc. So the length of this segment, curved segment on the circle, is called an arc. If I were to make the length of the arc exactly 1 unit, the exact same length as a radius, I wind up with an angle of about 57.14 degrees. There is a different way for measuring angles, and those are called radians. And the convenient fact about radians is that if the arc length is the same as the radius length, our angle theta is said to be 1 radian large. And the reason for that is because by definition, an angle theta is a comparison between the arc length and a radius. My theta looks a little funny here. It's theta. S is the arc length. And R is obviously the radius. So if I were to increase the arc length up to 2 on that same unit circle, I'm going to now have an angle that is 2 radians large. If I'm working on something that's not a unit circle, maybe the radius is 2. If I were to make my arc length 4, I'm at the exact same location on the circle, so the angle is still 2 radians. And again, that's because the definition is arc length divided by radius is the angle measure in radians. So let's go back to the unit circle. Zoom in. And let's put integer values for radians. So as I travel around the circle, I have 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, and 6 radians. And you can see that those are showing up on the diagram here. Here's 6 radians, and 5 radians, and 4 radians. An interesting thing happens when I take and bring my arc to create a semicircle. The angle turns into 3.14 radians, and we should know that 3.14 is pi. So one way of converting between radians and degrees is just to remember that a semicircle, or 180 degrees, is the same thing as pi radians. So the conversion factor is pi radians is the same as 180 degrees, or if you need to go the other way, 180 degrees is the same thing as pi radians. So we can use that to do these examples. If I needed to convert 45 degrees into radians, I'm going to take this and multiply it by something with degrees in the bottom, 180 degrees, and pi radians in the top. How many times does 45 go into 180? Well, I think that's 4 times. So 45 degrees becomes pi over 4 radians. Radians do not have units. Since an angle in radians is defined as an arc length divided by a radius, both of these would be measured in some length, maybe centimeters. Centimeters divided by centimeters cancels out. So an interesting property of radians is that they have no units, or are called dimensionless. Back to the examples. If I need to convert 270 degrees into radians, I'm going to take that exact same fraction, pi over 180, reduce where possible. 90 goes into both of these twice and 3 times. Again, the units cancel, so I get 3 pi over 2. And finally, this one doesn't have a degree symbol, so I'm converting out of radians and into degrees. I'm going to multiply by 180 degrees over pi radians. And if you notice, this time the fraction flip-flops because I want degrees to appear and radians to disappear. The pi's cancel. 4 goes into 180. 45 times. And 45 times 5 is 225 degrees. The last example, what angle is created when a 2.5 centimeter arc is drawn on a circle with a radius of 0.5 centimeters? If I'm looking for an angle, I'm going to compare arc length to radius. Arc length is 2.5 centimeters, radius is 0.5 centimeters, and that's 5. And again, there are no units, so we would just say leave it as 5, or maybe say 5 radians. The last topic is how to find the area of a sector. A sector is formed on a circle by drawing 2 radii and finding the area of the pi-shaped wedge between those 2 radii. I need the measure for the angle in radians, and if I move this point so that I have exactly 1 radian, I can observe that the area is 0.5. This is because the formula for the area of a sector is one half r squared theta, and theta must be in radians. You probably found the area of a circle using ratios and degrees. If theta is in radians, you can use this formula. Anyway, if I change the angle so that I have 2 radians, we can observe that 1 half r squared is just 1 half times 1 squared times the angle 2 radians. That gives me a total area of 1. We can see that this formula works even if I increase the radius to 2. Now that my radius is 2, 1 half r squared theta is 1 half, radius is 2, and my angle in radians is also 2. 2 squared is 4, half of that is 2, 2 times 2 is 4, I should get an area of 4, and that's what I see. So to work on an example, find the area of a sector with angle 45 degrees in a circle with radius 4. The first thing we need to do is change 45 degrees into radians. 45 degrees times, the conversion is, I need degrees to disappear, so I'm going to put 180 in the denominator, and I know that a semicircle, which is 180 degrees, is pi radians. The degrees units will cancel, so I'm going to be left with no units, which is good for radians, and 45 goes into 180 4 times. So 45 degrees is pi over 4, and that's my theta. The area formula is 1 half r squared theta. 1 half, I was told that the radius is 4 inches. 4 squared times pi over 4. And I get an exact area of 16. Cut in half is 8. 8 pi over 4 reduces to 2 pi. And so that's it. If we go back and look at the objectives for this section, we know that a radian is a new way of measuring an angle on a circle. We know that the radian is defined as the ratio between an arc length and a radius. And if you solve this for s, we know that the arc length is equal to radius times the angle measured in radians. We know how to convert back and forth between radian and degree because pi radians is the same thing as 180 degrees. So if you put that into a fraction, either pi over 180 or 180 over pi, you can convert between the two. And we know that the area formula for the sector of 1 half r squared theta. And again, theta must be in radians. It will not work in degrees. So in the next section, we'll talk about the difference between angular speed and linear speed, 2 ways of measuring how quickly something is moving on a circle.